Today's lesson is especially important because I'm going to show you how you're going to record numbers when you do measurements. And you're going to do this throughout the whole year. And you're also going to have to do this for the AP exam. They're probably going to give you at least one essay question where they're going to give you some data and you have to analyze the data and record your values, do some calculations. And so how you round them and how you record your measurements is going to be important. So first of all, when you're using a piece of equipment, you want to record digits that are certain. What I mean by that is if you look at this graduated cylinder down here, I know for sure that the value of this water level is between 2 and 3. So I can go ahead and put 2 because I know it's not going to be above 3. Then you want to look even closer so I can see that the tick marks, there's 10 tick marks between the 2 and the 3. So I know that each one is worth 0.1. And it looks like to me that the bottom of the meniscus, and be careful when you're recording liquid, you may have learned this, I can't really draw straight lines with the stylus, but the water makes a dip because water is attracted to the sides of the container. It's not quite as exaggerated as this, but if it was a dip like this one, and the question is, do you record it at the bottom of the dip or on the sides? And the answer is at the bottom. That's called the meniscus. So you'd want to look at the bottom of that and you want to get eye level with it. And then you would see where that red mark is recording, not up here where the edges are. So at the bottom of the meniscus, I can see that for this example down here, that it's somewhere between between 3 and 4. It looks to me like the bottom of the meniscus is kind of between the third tick mark and the fourth one. So I know that it's going to be 2.3 something. And then the last estimate, I just have to estimate, and it looks a little closer to 4 than 3. So I'm going to say 2.38. And what that tells scientists is that I know for sure the 2 and the 3, and this last digit is the one that's estimated. So if you record a value, and you may think from honors chemistry, if you record this versus this, that they're the same thing. And you're like, oh, it doesn't matter. They're both 1.2. And it does matter because the first one tells us that we're only accurate to the 10th place, and the second one says that we know all the way to the 100th place. So the more decimals you have, the more accurate your equipment is. And so that's why it's important. All right, let's look at accuracy versus precision. You probably remember these from honors chemistry, or at least you heard them. Most people in the real world use these interchangeably, but in science, it actually means two different things. Accurate is how close you are to the true value. So a lot of times in science, we will do a calculation first and say, at the end of this lab, based on how much we're starting with, we should end up with this much of our final product. And then we can compare when we actually do the lab and see how close we were. Precision is how close measurements are to each other. So this is kind of the word consistent would be used to describe this. And this is still important in science because when you do an experiment, you want to be able to perform it the same each time. So you want to be able to repeat yourself as you go through the experiment. So, and in fact, a lot of times in colleges, the professors or the faculty advisors will get their grad students to perform the experiments several times, even hundreds of times sometimes, to make sure they're getting the same result each time. We're going to get errors though. So there's always errors in every lab. And as we start to do lab write-ups, you'll have to include a source of error section in all of your lab write-ups. And the first thing that most high schoolers say is human error. And yes, there's human error. Yes, the equipment is not perfect. There could be errors with the balance or something, but those are going to happen in every lab. And it doesn't tell me that you understand specific to that lab. So we'll have to work on determining the errors in a particular lab that are going to affect your answers. And we'll even take it one step further because the AP exam loves to ask you about if this error happened, how would your final answer be affected? Like, would your answer be a little bit too high or a little bit too low? So random errors are ones that might be too high or too low, whereas systematic errors always include or always occur in the same direction. So this would be something like if your balance was not calibrated correctly, then you would always get numbers that were too high. Whereas a random error is for that particular lab, maybe you dumped out a little bit too much or something. So these are two different kinds of errors. And then the last 1% error is the way that scientists calculate. It's kind of like their grade when they do a lab. So it's actually the opposite of how you do your grades. So like if you take a test and you get an 80% on it, that means that you got 80% right, so your percent error is 20%. This is the opposite. So this is where you take the difference between what you were supposed to get, that's the accepted, versus what you actually got in the experiment. And these are just absolute value bars at the end. So just take the positive amount. It doesn't matter if you did too much or too little. We're just trying to see how far off you were. And then divided by what you're supposed to get times 100. So let's say you calculated that you were supposed to get 5 grams of your product and you only got 4 grams. So your experimental is the 4 and the accepted is the 5. So you would do 1 minus 4 is, or 5 minus 4 is 1. And if you just always do the bigger number minus the smaller number, you'll get the positive value. Divided by what you were supposed to get, and then times 100, we'll put it into percent. So this person had a 20% error. All right, that leads us to sig figs. So what we have to do now is to determine which of the digits in your answer actually show how accurate your equipment is, because some of the zeros or some of the numbers that you put in your answer are just placeholders. So for example, this 0 right here is not showing us how accurate that number is. So let's just do a few of these, and I'll show you my little trick for how to do sig figs, and then we'll practice some. So first of all, non-zero numbers are always significant. So if it's any number except 0, it's automatically important, and that counts as a sig fig. Sandwiched zeros and zeros to the right of the decimal are also significant. So notice in the first example, the 0 between the 5 and the 4, that counts as an important placeholder. And then in the next example, all of these zeros are after the decimal. Those are important as well. The zeros used as placeholders. So notice all of these zeros in all of those examples are placeholders. Those are not significant. And it's a little confusing because if you notice down here, the location of that decimal makes those zeros significant, and these are not. And at this point, you're probably like, oh my gosh, what is she talking about? I don't understand sig figs. Let me show you up here. So this is what my AP chemistry teacher taught me in high school, and it worked for me. So it's just a little trick. If you picture the United States, and you have the Atlantic Ocean on the right and the Pacific Ocean on the left, or east and west, whatever. So what you can do is think of A for absent and put it on the Atlantic Ocean side, and P for present and put it on the Pacific side. And when I say absent and present, I'm talking about the decimal itself. So if you can physically see the dot. And then you always start on the first non-zero number on that number. So if the decimal is present, you would start at the first non-zero number on the left because present is on the left. If it's absent, you start at the first non-zero number on the right because absent is on the right. And then you count towards the United States. So if it was present, you would count this direction. If it was absent, you count that direction. Here's what I'm talking about. Let's do some examples. Let's do okay, so for this first example, the first question you're going to ask is the decimal present or absent? It's present. I see the dot right after the 2. So I'm going to start with the first non-zero number on the left, and that number would be the 2. Then you're going to count towards the United States. Just think of the present Pacific Ocean, count towards the United States. So we're going to count all the way till we get to the end of the number. So all 4 of those digits are significant. Let's do another one. The next number, 500, the decimal is absent. I do not see a decimal there. So you're going to start on the first non-zero number on the right, since Atlantic Ocean is on the right of the United States. This first 0 over on the right is not a non-zero number. Neither is this one. So 5 is the first non-zero number on the right. And then again, you count towards the United States. So we're going to count to the left. There is nothing to the left. So all we have here is just one significant figure. Those 2 zeros after the 5 are not significant. All right, let's do another one. This one also is absent. I don't see the dot there. So when you see absent, think of Atlantic Ocean, which is on the right. So we're going to start with the first non-zero number on the right, and that is this 2. 0 is right here, but we're going to start with the 2 next to it. And then we're going to count towards the United States. So if we're on the Atlantic Ocean, we're going to count towards the left. So in this case, we have 1, 2, 3 digits that are significant. So the only one that's not significant there is that last 0. All right, and one more. So this last one, it is present. I can see the decimal. When you see present, you're going to think of Pacific Ocean and start with the first non-zero number on the left. The only non-zero number here is 3. And then you're going to count towards the United States, which is to the right. So we're going to count this way. So that last 0 is significant, but the other ones are not. So for your progress check today, it's a lot of practice with doing sig figs. So see if you can look at the numbers and determine how many significant figures they have. And don't forget to check your answers. There's a few more things real quick. When we're doing math with sig figs, there are 2 different ways to do it, depending on whether you're adding and subtracting or multiplying and dividing. So adding and subtracting, the rule is that you add your numbers and then round them to the least number of decimal places that you started with. So here's what I mean by that. In this first number, we have 3 numbers after the decimal. In the second one, we have 2 numbers after the decimal. 2.589 is 3. 9.1 is just 1. So notice that of all of those that I just did underlines for, this one only has 1 place after the decimal, and that's the lowest. So that's what you have to round your answer to. So we want to round it to this place. Then you have to look at the number after it to see if you round up or down. So 8.6, 6 is greater than 5, so you're going to round that up, and that's how they ended up with this answer. All right, multiplying and dividing, you're not looking at decimal places, you're looking at sig figs. It's kind of like your answer is only as accurate as your least accurate piece of equipment, kind of like the weakest link, that you're only as strong as your weakest link. So when we are multiplying, we're going to first type all this in your calculator and you end up with this number here. Then you're going to look back at your numbers and see how many sig figs you had. So 2.87, all 3 of those are significant. 18.62, all of those are significant, and 9.3, all of those are significant. Remember, zeros are the only ones that are questionable. So of those, 2 is the smallest, so I need to round this to a number that is only 2 significant figures. And the easiest way to do that is to put your number into scientific notation and then to chop it off where you need to chop it off. So if we put this into scientific notation, we would have 4.9698,642 times 10 to the second. So then you can just chop it off. We needed to only have 2 sig figs, so chop it here. But notice that 6 is higher than 5, so that's why it rounded the 9 up, which then rounds the 4 up. And so that's how we got this final answer. And again, you can practice that in the progress check, and then we'll go over the answers as well. The rules for rounding are that you should round for each step. However, it is acceptable to round at the end of a series of calculations. So instead of rounding at every single post in the fence, you can just type it all in and then round at the very end. And what I tell my students is just double check that your answer, look back at your original numbers and make sure that it matches the right number of sig figs. Be careful here. Some of you are going to say, do we need to be careful about sig figs on a quiz or a test? And the answer will always be yes. So from now on, every time you do a calculation for this class, you need to go ahead and get in the habit of figuring out your sig figs. So let's just do these 2 examples. We have, the first one is 5.4 plus 2.3 plus 2, and that answer is 9.7. Then we need to round it. This one has 3 places after the decimal. This has 1. This one has none. So our answer cannot have any numbers after the decimal. So we do need to round that because we need to get rid of the 7, and it's going to round the 9 up, so we can round that number to 10. And then this one down here, so we have 4.1. Do your order of operations. Please excuse my dear Aunt Sally. So do your subtraction first, and you get 3.92. Then we need to round that appropriately. So this one has 1 place after the decimal, this one is 2. So we need to round this to only 1 place after the decimal. So I'm going to get rid of that too. Now we can do the next step. So 3.9 times 42, that answer is 163.8 in the calculator. But then we need to do the math for that and look at sig figs. 42 is 2 sig figs, 3.9 is also 2 sig figs. So again, the easiest way to get it into the right number of significant figures is to put it into scientific notation. I already rounded this one. Put it into scientific notation and then times 10 to the second, and then chop off the digits you don't need. So we only want 2 digits, so we're going to chop it here. 4 does not round the 6 up, so our final answer is just 1.6 times 10 to the negative 2. I'm sorry, positive 2. All right, and one more small section for today is temperature. So you will have to do quite a few temperature calculations for this class. Most of the time you're going to do Celsius to Kelvin and or backwards. So these two are the ones that you'll use most often. And you don't need to memorize that 273 number. It's in your reference packet. And then the last thing is just if you happen to go from Celsius to Fahrenheit or backwards, you can do it. You just have to use an equation. So if you have Fahrenheit, you're going to subtract 32 first and then multiply by 5/9